Wei here. This is a heuristic approaches to the traveling salesman problem, which is the project topic we have chosen. It is also a comparative study of the two algorithms that we have chosen to solve this problem, namely the nearest neighbor and greedy search algorithms. This is the project group members. And for the introduction of the traveling salesman problem, so there is a salesman who needs to visit several cities, and the challenge is to find the shortest route that lets him visit each city only once and return to where he started. So this problem may seem simple on the surface, but the primary challenge of this problem lies in the exponential amount of possible routes. So it is impractical to evaluate every possibility in large data sets due to the exponential factor of it. So to tackle this problem, we are focusing on two heuristic approaches, namely the greedy search and nearest neighbor algorithm. So for greedy search, it builds a route by selecting the shortest possible edge at each step, regardless of the overall impact on the solution. So basically, what that does is it selects the shortest available path to an unvisited node. Um, for nearest neighbor, so we start from any random city and repeatedly visit the nearest unvisited city to form a path based on the proximity. So basically, it visits the closest unvisited node.
Hi, my name is Chan Jingshan, and I'll be going through the objective of our project, which focuses on analyzing and comparing the two search algorithms, the greedy search and the nearest neighbor algorithm. First, our primary goal is to implement both algorithms on a defined problem space. This hands-on approach allows us to study their behaviors directly and fairly under the same conditions. Second, we aim to evaluate the effectiveness of each algorithm. We'll do this by looking at the solution quality, like how optimal their solutions are, and computational efficiency, meaning how quickly and resourcefully they arrive at those solutions. Thirdly, we want to identify specific scenarios where one algorithm performs better than the other. Different problems may favor different approaches, and understanding that can help in selecting the right tool for future applications. Finally, we seek to gain deeper insights into the strengths and the limitations of both algorithms. This comparative understanding is critical not only for this project, but also for broader decision making in AI and search strategy design. And now I'll hand it over to Harini, who will walk you through the research background and give you more context about the algorithms we selected.
Hello everyone. I'll be going through the research section of the traveling salesman problem. Traveling salesman problem is a classic challenge in computer science and operation research. The goal of this is to find the shortest route that visits each city once and returns to the start. It's modeled using graph theory. Cities are nodes, routes are weighted edges. Why traveling salesman problem is hard? Traveling salesman problem is a NP hard, which means no known algorithm solves all cases efficiently. The route combinations grow fractionally with cities. Exclusive search becomes impractical as city count increases. How to tackle it? Use heuristic algorithm for huge enough and fast solutions. The popular methods include greedy search and nearest neighbor. Greedy search algorithm. It chooses the best immediate option at each step. In traveling salesman problem context, it selects the shortest available path to any unvisited node. It avoids revisiting states or forming cycles. It's simple, fast, and intuitive. How it works. There's no look ahead or backtracking. It prioritizes local optimality in hopes of global optimality. Very efficient on large graphs. In terms of theoretical insights, it's fast but may give suboptimal routes, doesn't revisit decisions, can make better overall paths. These are often used as a starting point for genetic algorithms, stimulated annealing, other meta heuristics. When to use? When speed is critical for generating quick feasible path as input to refinement algorithm.
Hi, I'm Tibing. Now I'm going to go through our next research topic, which is nearest neighbor algorithm. So nearest neighbor is a greedy algorithm that builds a route by always visiting the closest unvisited city. Then it repeats this until all cities are visited and it ends by returning to the starting city. So how does this nearest neighbor algorithm work? So in a nutshell, is to go from the current city, from your current city, go to the nearest one that you haven't visited yet, and then it will go to the next nearest one. So it's actually like a step-by-step construction of the route, and it's simple and easy to implement, and then it prioritizes local proximity. So for the theoretical background for this nearest neighbor algorithm, so this is deterministic because it has the same input and the start point, so it has the same output, and it has the time complexity of O(n) square, which is fast for mid-sized data set, and but then it has some trade-off. It can produce path up to 25% longer than the optimal, especially in Euclidean space, and there is no backtracking or optimization of early choices. Like those cities that you have actually went to first, you cannot actually backtrack to them. Then, when to use the nearest neighbor algorithm is for quick approximate solutions. It is as a baseline for comparing with other algorithms and a starting path for further optimization techniques.
Nicholas here. So I'll be going through the datasets and our implementation. So for our datasets, we'll be using these four different sets of data: tiny, small, medium, and large. On the right side, we can see a simple visualization of each of the datasets. If you look at the tiny dataset, actually it has only 10 records, and based on the graph, it looks quite simple. Then for the large dataset, it actually has 1,000 records and looks very clustered. Okay, so moving on to our implementation, we'll be using the nearest neighbor search and the greedy search. The nearest neighbor search actually starts at a random chosen city, repeatedly visits the nearest unvisited city until all of the cities are visited, and then returns back to the starting point. While the greedy search iteratively adds the shortest available edge that doesn't form a cycle or revisit a node prematurely, and also ensures a complete route is built based on the locally optimal edge choices. So moving on to the comparison between the both of the search algorithms, as we can see, we are basing our results on the execution timing and also the minimum distance found. As you can see from this table, right, the nearest neighbor is actually generally faster based on our findings on the medium and large data sets as compared to the greedy search. And if we are looking at the minimum distance, the greedy search is actually better at finding the better routes when while working on larger data sets. So in the next two slides, right, we'll be going more in depth into these results.
So based on our implementation, the results suggest that while greedy search is more often considered efficient, nearest neighbor can sometimes outperform it in execution speed, especially on dataset where its proximity-based decisions reduce unnecessary computations. So you can see on the graph on the right-hand side, the greedy search has faster execution times on teeny and small datasets. For medium dataset, nearest neighbor was marginally faster, and on the large dataset, nearest neighbor again performs slightly faster than greedy algorithm, showing that the nearest neighbor can scale efficiently in terms of runtime. The nearest neighbor performs shorter routes in tiny and medium datasets. Then for greedy, produce shorter routes in the small and large datasets. Nearest neighbor is more efficient for small graphs due to its simplicity and deterministic nature. As the dataset increases, the greedy search demonstrated better performance in finding more efficient routes.
Hi everyone, I'm Xiao Feng, and this is our conclusion. The traveling salesman problem is classic challenge in optimization and algorithm design. Exact solutions are computationally expensive. We explore heuristic approaches to find practical, near optimal routes using greedy search and nearest neighbor. We used and compared two simple algorithms: nearest neighbor, which is fast, simple, but prone to local minima; greedy search, which is slow but better in complex datasets. We focus to achieve a balance between performance, which is speed, and solution quality, which is accuracy. Greedy search is more effective at producing shorter routes in larger or more complex datasets, but it does take a little longer time to compute. Nearest neighbor is faster overall and performs well in smaller datasets, where its simple logic provides competitive solutions quickly. Both algorithms offer practical heuristic approaches for solving difficult traveling salesman problems, with greedy search offering better scalability and route optimization in larger datasets.